Hi everyone. Today I would like to talk about how to do deep learning in about 5 lines of code with a pretty cool library called FastAI. Now, a big caution that ML is not that simple. Those 5 lines I'm talking to refer purely to the training aspect, and even then, there are much more things to be done apart from just specifying the model and just training it. As this very cool diagram for from Google points out, the 5 lines of code I'm talking about is part of this square, but there's much more things to be done in an actual ML project. So even just getting a model to have just 5 lines of code is pretty impressive. How have we come to this point that we can get very complex predictions with such few lines of code? The trick here is a concept called transfer learning. Now, in transfer learning, we have these organizations with deep pockets who have the resources to train a generic model on huge amounts of data, taking perhaps weeks of training time or hundreds of thousands of dollars of resources to train a model for a generic task. Transfer learning is me being able to have a particular task which is totally different from what that generic model was trained for, but me being able to customize or tweak it to my particular task at a fraction of cost and time and get all the benefits of the training done for the generic task. Now, before we go into how transfer learning happens in general, let me start a bit more from the basics. Just to give you an idea, this is not to go very in depth into what deep learning is, but to just give you enough of an idea so you can understand that those 5 lines of code. Now, deep learning is another term for what was previously called artificial neural networks. So if you imagine when you have inputs as text or as images, these are converted into numbers and fed into an input layer of a model, which is the blue lines over here. Now, let's say we talk in the context of predicting if a particular image is a cat or a dog, then the image gets converted to numbers. Over here, we do some magic here, and then we get the output in this yellow square as is a cat or dog with some probabilities. What I glossed over is this concept of a hidden layer. So imagine this vertical line of green to be one layer and this to be a second layer. Deep learning refers to the fact that we can technically not just have 2 layers, we can have 100 layers, 200 layers stacked one after the other, and it is the connections between them in many ways that captures the complex relationships between in a particular image, for example, which will let us determine if it's a cat or a dog. Now, these lines over here are basically numbers being passed or propagated from one layer to another. But what happens? What do these numbers mean, and how does each layer affect the subsequent layer, a layer after it? Now imagine that circle to be so many small nodes in the previous diagram, and let's imagine we look at one particular node. Now, whenever some input comes to this node as numbers, we multiply each input with some weights, and how we calculate these weights will be explained later. But imagine that we've already figured out the model, and now a new image has come to us, and we want to know if it's a cat or a dog. So when the new image is converted to numbers, for example, x1 and x2, disregard this one for now. we multiply with some weights, as you can see over here, w into x1, w2 into x2, and so on, some bias number which we won't get into. And then we use some kind of a function which depends on the model, and this will then trigger an output. And the intuition is that these weights, they capture certain aspects of the kind of image or kind of decision you want to make on the image. And if for some particular nodes in the layer will have weights for one particular aspect of the image. So let me see if I can explain that part in the next slide. So let's get into an example of how a deep learning network is able to identify whether a particular image is a cat or a dog. We start with a very simple neural network called AlexNet, and which has only got 5 layers. Now, what Matthew Zeiler and Rob Fergus kind of found out is that the layers at the beginning kind of understand simple structures or simple structures like lines, for example, as you can see over here. And then as you go to the subsequent layer and so on, each different layer is able to capture more and more complex patterns. Now, talking about layer 1, for example, now layer 1, like if you look at over here, this is what triggers layer 1. Like if you remember the output y of before over here, we are kind of showing what that particular layer gets triggered by for when a particular image comes in. So the images are shown at the bottom over here. Now, for example, you can see that these images have a diagonal line, and you will see over here that these diagonal line images will trigger this particular layer because this layer is only trained for lines. But as you go a bit further into the other layer, like layer 2, now this can detect a bit more complexity, like corners, repeating lines, circles, and other simple patterns. For example, if I look at this over here, this tire of the circle, you can see, I hope so, that there's a slight curve over here trying to be able to capture that kind of pattern. And this goes on and on. The third layer is able to capture car wheels, text, and flower petals, and even complex patterns like repeating shapes over here. Like if you see this tile over here, it's able to capture the tile over here as well. And the subsequent layers are able to capture things like a dog's face. For example, if you look over here, there's a dog here, and the fourth layer is able to kind of capture this pattern over here, and so on and so on. Finally, when we come to the face of people, like we see the woman here, you can see that it's able to capture the face of the woman here. Now, this is AlexNet, which had 5 layers, and as you can see, it's still pretty impressive. But today's models have hundreds and hundreds of layers. So you can just imagine how complex or how sophisticated our deep learning models can be. So now that you know about layers, let's see what transfer learning is. So in this particular example, what we are generally talking about is that there is some pre-trained model that was trained on some genetic data set, for example, in this case, the ImageNet data set. And it was trained and some classes were figured out. Now, I'm not that good at diagrams, so I copied somebody else's diagram. But imagine that this was class 1 was a woman, class 2 was a dog, and so on and so on. Now, Imagine that I had a particular use case where I was given images which are never there in this ImageNet, and these are my own private images of tissue samples, where we're learning to find out if the cells on this tissue have a particular kind of tumor or not. Now, this are labeled like H and T, where they mean something for a particular tumor or not, and I won't go into the specifics, but you can understand that I don't have, may probably not have a lot of samples for this compared to the thousands and thousands of pictures here. So what I can do is I can take this pre-trained model and I can customize it for my particular use case. So the way we do it is we first take this model, and as you remember in the AlexNet example, the initial layers were able to capture more fundamental elements of a picture, for example. So these things will also be useful for my particular use case of tissue samples. So if that is the case, we don't need to change the weights of the initial layers. We'll keep them as they are. But in order to customize it, we will replace the last layers of the pre-trained model with our layers. But what you have to understand is that the ones in the blue signify that these are layers with actual weights stored in them. And the orange layers basically mean it's like a blueprint, but we don't have any weights so far. And then when we now will add our data set and try to train, let's say I have only 100 pictures, I will try to train this model with those 100 pictures to figure out the weights for this last 3 or 4 layers that we added to customize it to our problem. Now the way we tweak this is called backpropagation, and that's another way of how the way I understand backpropagation is that it's like a smart trial and error. Now, when we do something, we are tinkering, we make a mistake, we try something else, I'm calling that trial and error. What I mean by smart trial and error is that every time we make a mistake, we have some inkling what to do next, which avenue to go. Should I turn left or should I turn right? For example, that kind of inkling is what I call smart trial and error, and the fancy term for that is backpropagation. I'll explain this a bit more in depth later in the slides coming forward. That was given from that paper. So as you can see, if we have these pre-trained models, it makes it much more simpler for us to customize it to our particular use case. And there are many pre-trained models right now. And what's impressive is that we even have domain-specific pre-trained models like MedSpacey, which is a library for clinical NLP or clinical by NLP I mean text, where we look at, for example, a review online and we can predict and say it's a positive review or negative review. So all text-based predictions are called NLP. And we even have pre-trained models for medical terms to make our life easier when we make models based on medical data. So that, in summary, was what transfer learning was. And what we now want to talk about is, okay, that's transfer learning. What does FastAI do? FastAI takes transfer learning and its design takes it to a different level. It has very well thought out abstractions for deep learning, which make life very easy for the practitioner. So let's look at some code examples, and I'll try to walk it out step by step. So The code over here, it installs something called Fastbook. Fastbook is just a library for the Python code that supports a book that actually accompanies FastAI, but that's what I use as well to set up my notebook. So you'll see I install Fastbook, and when you do that, you also get the library FastAI. And since the example I have for you is about vision, I am importing all the methods of FastAI for vision. Display is just a function for me to help show things easily for you. So let's talk about the problem where we are given images of pets and have to classify it as a cat or a dog. So FastAI already has some links. So for that we can use and prototype quickly. For example, if you see a link over here, I displayed, and this is actually some zipped file of all the pet images on the S3 service in Amazon. And after I untar it, again, a very useful helper method from FastAI, and I check it out, I can see that there are many images over there, all in this folder images. Now, just a piece of caution, if you have normal Python and you see path.ls, this won't work. FastAI does do some kind of special magic to add new methods to the path object, like adding a new method called ls. Uh, that's not within the scope to explain how they do it, but just be careful sometimes to see that FastAI can sometimes add special methods. So just to give you how they have done these things, so if you look at these two images, the way they have set it up is that if the final name of that image is lowercase, like over here E is lowercase, then it's a dog. But if the name starts with uppercase, it is a cat. So this is useful for us because in training, we have to give it the raw data, but we also have to give it the labels to whether for the model to know if a particular image is cat and dog for it, so I can train the model. So if you play with it, if I create a path object, for example, I look at the stem, I get this Sphinx 146. Okay, then I can play with it further to capture and see how do I figure out, how do I programmatically tell FastAI if something's a cat or a dog. And the way I do that is with this function where I take the path, I take the stem, as you saw, it was the name of the file. I pick the first letter and I check if it's upper or not. If it is an uppercase letter, then it is a cat. And as you can see, I'm just calling this cat function here with that variable we had before and return back true. Now, previously we did see all these paths like this before again, but I'm just going to show you another helper method in FastAI called getImageFiles, which gives you all the images. And the difference is that this particular method, for example, will recursively go through a folder and get all the images, which is pretty handy because sometimes the raw data can be segmented in different folders. So let's come to the first concept in training. When you have, for example, 100 images, you do not send the entire thing for training. The problem with that is if you send all the images to training, in a way the model can cheat because it can literally say if you send a new image to it, or if you send an image from the same collection actually, it will say I've all these things before, I know how to deal with it, and it'll give you back the right answer. The problem is this works very well when you're playing with it, but if you send a new image which the model hasn't seen at all, it will perform badly. So we want to prevent that from happening for a model. So what we do is, if I have 100 images, I won't use all for training. I'll only probably use, example, 80% of it for training. And after the training process is done, I'm going to check, I'm going to validate how well the training was on the 20% of the pictures I did not send for training. And that way I can honestly know if the training was really good or not. So the way we do that in FastAI is that we use something called a random splitter. Now, if you see, I'm trying to display what a splitter is, and it's actually a function, which is a bit unintuitive in a way, because normally when I look at Python, I'll see, if I see words from capital R and capital S, for example, I normally think of a type or a class, but it's good to know. This is a way of figuring out for sure what it is, and it's a function. Now, a random splitter will take mostly a collection of images and then randomly split it across different two buckets, one the training bucket and the validation bucket. Remember we talked about 80-20% split. What we're basically saying over here is that the validation percentage is 0.2 or 20%. Now the next part is an interesting thing to know. Normally, if I did not give this and I did the random splitter, every time I ran the splitter, it would give a different collection of images in the 80% bucket and the 20% bucket. But sometimes when we are playing with things, we want some kind of determinism, like reproducibility, to have the same output all the time. So we normally give a seed. And I'm just giving a random number called 42. Now, just to see how it works, let's say I'm taking if you remember, images was all the images in a data set. I'm just giving it the first 10 images, and I give it to splitter. And what splitter does is it will split the indexes of that list of, so this is technically a list of 10 images. It will split the indexes into a bucket for training and another for validation. So this is 8 over here and 2 over here, right? 80-20% split. If I call it again, because I'm giving it a seed, it'll return back the same indexes or indices for the split. If I didn't have a seed, if I call it again over here, it would give a different list. So now we have split, or we know how to split it into two different. We haven't split it yet. We've just created the functionality to split at the right moment. The main part, or I would say the main value of the FastAI abstraction is something called data blocks. But before I get there, let me talk about a hypothetical library, like, oh, my cool library, and what I expect from this library. Now, I would expect that to be a train method in this library, and the general format I would give it is, I would say, okay, the type of thing I'm giving to you as input is an image. What I want from you is a yes or no kind of answer, or a categorical answer. So that we specify it to be a category. I'll give you the raw data, that is the images. I'll give you the labels. If you remember, labels to be, is it a cat or a dog? We had a function, if you remember, called isCat, which helps us figure these labels out. And we give the splitter that you've seen just previously to be able to split the data. And we'll also give it something which we call a model blueprint, which I'll explain much more later. And then the training process will take all of this and give back the model blueprint, but will also figure out the weights. Training is all about figuring out what the weights will be for each of the node in the layers. So before we go, let's go step by step. Now we're talking about training, and I talked about this input type. We want to specify that the input type is an image and the output type is a category. How do we do that in FastAI? So I'm just slowly building up. Just for to show you what they are, let's imagine I made some function called add, right? It takes a and b and returns back a plus b. If I try to display what add is a function which takes a and b as input. Similarly, because we imported all the constructors of FastAI, we also have, instead of specifying it as input type image, we can have these two things called image block and category block, where we're saying that the input could be an image block and the output is a category block. And if I do display on them in a very similar manner as add, you will see that they also are functions as well, which probably take some input and take some output. Now, perhaps some people may prefer it to be like this, but if I had to guess why FastAI does it this way, is that it wants to be able to allow the user to customize uh, the type of input to things perhaps that FastAI may not have seen before. And the benefit of doing it this way is that we can add blocks outside FastAI without changing FastAI. At least that is my guess. So now we talked about how to specify the categories. This is the key structure that I was talking about called data block. And the data block is just a specification, a format for how the model should expect, one, the input data coming in, and two, how to do some kind of pre-processing or transformations before trying to figure out the weights. So the way we do it is we specify something called data block. I've already showed you the image block and the category block, and this is very similar to these two lines over here where we're saying the input is the images and the output is a category true or false, for example. We already showed you get image files. It's that helper method which takes probably a path and returns back all the images there. We already showed you a scat, which would probably be used as a function to read a path and get back if it's a cat or not, true or false. So I've used different terms. I've called them labels perhaps, but they're also called ground truth. And they're also called the y variable when the input is then called the x variables or features. I already explained what the splitter is. It'll take the data, whatever comes in, and it will split it according to the 80-20% rule that we gave. And I haven't explained this part, but this is an example of transformations run on the input data coming in before it's passed to the model. In this particular case, we are predicting on images, and images can be of different sizes and shapes. And models don't like that. Models want a fixed size and shape. So what we're saying over here, for example, is that every image coming in, we resize it to a standard 224 pixel width and height. So if you notice over here, nothing over here is talking about the path that has all the images. That'll come later. This is purely a specification of how to understand data coming in and what transformations to do. So once you get that D block, we then give it the actual path and we construct a new concept, a new FastAI concept called data loader. Now, data loader is what is actually passed to the training process to get the files or the images from the file path, and its actual value is that it's able to provide images at a batch instead of taking it at a batch which is suitable for the GPU, and it will just get you things in the batch for both the training and the validation set. So we talked about the input type, output type, images, labels, and splitter. Now let's come and talk about the model blueprint. The model blueprint is, in simple terms, a structure of a deep learning network without any weights. It's like an empty shell that we want to fill up, and we want the training process to fill up with the right weights for our particular task. One of the examples we are going to use is a popular architecture or a model blueprint for image classification called ResNet. I won't go too much into the details of it, but ResNet is 18, for example, is one. There are 18 layers if you count this barring some. And these layers are a bit more complex than I showed you, but you can, for the sake of discussion, see them as simple layers. So when we say we want an architecture, we specify saying, I want the ResNet architecture. Now, FastAI already has all of these things as part of its library. So if I just type ResNet 18, for example, you will see that's actually a function already in FastAI. And as I said, a ResNet 18 in this case is seen as a model blueprint or an architecture. And you will see that it's supposed to have weights, but it's optional. And what that means is that if we don't provide these weights by ourselves, these weights are already specified because, as you know, we are in transfer learning. We already have these weights because somebody did that for us. And if we don't specify any weights, FastAI will automatically pull the weights that somebody else trained for previously. So let's see what those weights are. So as you can see over here, it's a PTH file, it's a PyTorch file, and these are the default weights if you don't specify any weights for ResNet 18. The next step is, okay, we've got a model blueprint, we've got default weights, and now we want to fine tune this to our particular task. How do you know that this training is doing a good job? The way we do, as I said, is when we have training, we will train it on, for example, 80% of the data set, and then we will test it on the validation set. And in some way, we are trying to check the accuracy of of that data. So if the validation set had 10 images, for example, we would take, so if we got 2 wrong, we would say its accuracy is 8 out of 10. Or we could also have the reverse, and we can say the error rate is 2 out of 10, accuracy being 8 out of 10. The job of this is to map this accuracy concept to something which is important to us humans. The accuracy metric, for example, it being correct 8 out of 10 is something we as humans intuitively understand and makes sense for us, and we can understand and see, okay, this is getting better or worse. So some first might say, okay, that when you say for humans, does that mean we have a separate metric for machines? And that is correct. We don't use this metric for the training part. If you just clarify, we use this metric to assess it on the validation set. But it would be nice to say, okay, let's use this metric during the training, and let's see how wrong we are with the smart trial and error. But the problem is that these metrics, which are great for humans, are not very great for machines when they're training. Because, yeah, they give you an idea of you're wrong and you're how wrong, but it does not give you any help to say where to go next. And so instead of metrics, for the training part, we use something called a loss function. I won't go too deep into the loss function, but the idea is that one, it'll tell you, okay, you're wrong, but it'll also tell you where to go next. And a good way of understanding this is the hot and cold game some of us have played as kids. The idea is that when somebody hides some special thing, and then you have somebody who's a guide in the team, in the opposite team, and then a seeker. And the guide will tell the seeker where to go, but he can only say things like hot, cold, warm, lukewarm, and so on. So when someone is the seeker first has no clue where to go, he'll take a step, and the guy will say warm. Okay, then the seeker knows, okay, I have to go in this direction, but I don't know how big a step to take. I'm going to take another small step. And the guy will say hot or warm again. So now the the seeker says, okay, I've got two steps, both are warm. I can be more confident. The next time I'll take a bigger step. And then if the person says warm again, okay, I'm on the right path, I'm going to take a bigger step and a bigger step. So that is why I call smart trial and error. It tells you if you're hot or cold, but it also tells you in terms of temperature. Like, okay, warm, warm. And if you're very close to the treasure, the guide may say hot, hot, hot. So then now you will try to take smaller steps because you don't want to go too far away from the treasure. You want to be very close to it. So that way you are able to check out how big a step should be based on hot, cold, and warm. And this is what exactly loss function does in deep learning. So the metric we are going to use in this example is not accuracy, but the opposite of accuracy called error rate. That is, how much did we get wrong in the validation set? And I won't go too deep into it, but the loss function we're going to use is something called cross entropy loss. So this defaults mostly used in classification. So if I display this, you will see that these are, again, if I display error rate, it's a function. If I display cross entropy func, it's actually a class. So now we come to defining the learner. So we're not actually learning yet, but we're just defining the learning process. If you remember, we had the data block and we give the data block to a data loader, which will give things to the process in a batch. For example, for our GPU, we talked about ResNet 18, which was generally the model architecture, but we also said, okay, let's pick up the default weights, which we learned from, which we will pick up for ResNet 18, what somebody has trained before. We talked about the metrics, that is the error rate, and the loss function. Now, just to clarify, loss function is not required. It picks up the loss function automatically from the data given to the data block object. But I just wanted to show you because you will also see it later on when doing the training process. Now, I talk about train just to, but there's actually we're not literally training, because the idea of training is it's generally used for when you're trying to train a model from scratch. And it's also in machine learning world called fit. That in a sense, we have a model architecture and we're trying to fit new weights to a model architecture. But as you know, in transfer learning, we already have a pre-trained model. We're just going to tweak it a bit. We just want to, remove the last few layers, add our layers, and we just want to tweak it. And the term used in machine learning world is fine-tune. So that's something we need to know, that we are not really training something from scratch again, that we are going to actually fine-tuning it to our needs. So when you have a learn object and you call fine-tune, that's what's happening. It's basically tweaking. There's a lot of things happening below the hood, under the hood. But over here, we are saying for sake of illustration, fine tune it for one iteration, or also called epoch in the machine learning world. So we are 40 minutes in. I'm sure I only have my mom listening right now, but I'm sure she must have slept as well. Let's look at the code. So this is the code and the file line. So I'm not, again, as you see, we import FastAI, we untar. I'm not counting this as training code, but it's over here. That's the 5 lines of code. And as you can see, I lied. It's not 5 lines of code. It's actually 4. But it's still, these lines of code are not what you've seen before, not what I explained, but this is a wrapper over the concept I explained to you before, but they are still very similar. For example, you remember the iscat. This is a slightly different method, but it's a very similar concept. We have data loaders, but we have these helper functions which know about or are used in very common use cases. But you've seen these things before. You've seen the path, you've seen get image files, you've seen the validation percentage, the seed, etc. And I've laid it out in a very detailed format for you, but in reality, all of that is hidden to you in these 5 lines of code. And ultimately, you do get a data loader, and you give it to a vision learner the same way we did last time. If you remember, we give the data loader, the model architecture, and the metrics, and then we fine tune. And as you can see, it's just these 5 lines of code. When you run this, it'll first run one iteration of one epoch just to set things up a bit. But since he said we want to fine tune for one more iteration of one more epoch, it will just run this, and you can see while it's doing that what it outputs out, and I'll explain this in a second. But just to clarify, you normally would do it for more than one epoch. I'm just showing you as an example here. So what do we see from after the end of one tuning for one epoch? If you remember the loss function, that is used to help the training process come and figure out, okay, we got all this data, how do I do smart trial and error? And in the first iteration, you will see that it comes back with some kind of training loss. And then for the validation loss, it tests the same thing, but on the validation data set. And the idea is that you want this thing to come down. The error rate is for us to figure out, to get a sense of intuitive sense when you look at it, okay, is the error rate coming down or not? But you see, this is for us, for our consumption, and this is for the automated training process to use to bring down their mistakes. So once let's say we did that for many iterations, not just one, and it's over, I just want to show you how to use it. So we're going to take one image again from this images list that you remember. This is just a presentation. Normally you never select an image from the existing data set. You always predict on, in the real life scenarios, you predict on new images that they have never seen. But over here, just to show you, for example, we will take a path, we will create a image format, and you can see over here it's a dog. And then disregard this line, but if you remember the learn.finetune, it's the same learn object. We actually ask it to predict this image, and it gives back 3 different values. The first one is a Boolean. So if you see print iscat, it'll say it's false, which makes sense because we gave it a dog image. And then the category is 0, and this is actually an index into the probability. So if I see print probabilities, it's over here. There are 2 of them because we only want cat or dog. And this category says 0. So this is 0, this is 1. And it says that this is most likely what the category is, and this basically is one, and that's what you see. Like if you do props category, you get back one. So this is basically saying that we think it is a strong probability of one that it's a dog. So that was a long lecture on the abstractions of FastAI, and they're pretty versatile. They can be used for many other things, not just images. The second thing I wanted to talk about how cool FastAI is this idea like of designing the entire framework for a notebook based experimentation experience. And what do I mean by that? If you remember that data loader that I showed you, you have these different functions. I mean, for example, uh, you have this show batch, which kind of makes it easy for you to analyze your data and see what it is. For example, if you do a show batch for 9, it'll show you that this is a dog, so a false is not a cat, right? And this is a cat, so it's true. So they have these functions in them that help you interact with the data in a notebook and make it much more easier. A few more examples, and many more. The other examples I have is that you also have a cleaner. Now, a cleaner will basically help you sometimes to, normally in many cases, you'd clean the data before you send to the model, but there's a cool technique I've seen FastAI use that they actually use the model to clean the data for them, and they probably go back and run the model again. So what does that mean? So if you use this image classify cleaner and you say clean, and you give the learn object, it gives you this example, these things that you can say, hey, we're looking for all black. Now, this is black, or you want to keep this image or not. Okay, I had to pause for a bit because the first image threw me off a bit. But the first image actually has two images in it. So it is an example of something you don't want to keep because it's going to screw up your training. So FastAI has these UI widgets that can allow you to keep and or delete, and you have this, and you can what you can go and do in the notebook. This is a snapshot. You can decide keep and so on, and then later on you can actually delete all the data that you want, which you don't want anymore. You can change the labels, and FastAI will automatically do that for you. It's just these two lines of code. The other example I like is it allows you to interact and find out what are your top errors. So in this particular example, there's not, I should have specified, yeah, I moved from cats and dogs to bears because I couldn't get this working on my machine for cats and dogs. So this is all snapshots. But in this particular scenario, we are trying to predict if a particular bear is either a black or a grizzly or a teddy. So that is the image classification scenario. And what you can see over here is that if you have these top losses, the first one is what the model predicted. The second one, what it actually was, like the label, the ground truth. The third one is the loss. And the loss is a measure of two things. One, how wrong we are, we are, or how different we are, how wrong we are from what is supposed to be, but also how confident we are when we are wrong. So if I predict something to be wrong, and I'm extremely confident, when I say confident, it's the probability, and I'm saying I'm extremely confident about this prediction and it was actually wrong, then the loss is much higher. Now, to take an example over here, we predicted grizzly with an extreme confidence of 0.74 out of 1. It was actually a black. So the loss takes these two things into account and is extremely high. So this is the image that we the got it wrong the most. Now over here, we predicted a grizzly to be black with a probability of 61, less confident than this, so our loss is lesser than this. Over here, we predicted black, but we are predicted, but our confidence was extremely low. So even that is taken into consideration. Even if we got it right, we were not very confident. So in that's taken into consideration when we talk about our loss. That's why it's shown in our top losses. So yeah, that was just a few examples of how FastAI uses the notebook to really make it very interactive for you to play with your data set and to play with the output of your model to make you make a better model or to understand your data set. It's got very top-down approach, unlike me, in the sense that it will try to teach you how to get things done first, which is very useful. It gives you instant feedback. You feel very confident about what you've done, but it does go into deep much later in later chapters. The defaults are just amazing. They are from years of experience. The creator was a previous Kaggle grandmaster. If you don't know, Kaggle is a competition for data science. So it feels like FastAI has been designed taking into account all these different things that one needs to know, which you normally would not know as a beginner. And under the hood, it also does a lot of heavy lifting. For example, transfer learning, optimized batch normalization training. Now, I have no clue right now what that means, but I was just trying to impress you on the behalf of FastAI to know that it does a lot of heavy lifting under the hood that we normally don't see, and that's much appreciated. Also, in addition to that, it's got a very supportive community on Discord and forums, and all the resources explaining all those things that I have talked to you about in much more depth is free online. So, yeah, the next steps, you can go and get the resource, the book itself. The book is paid, but all the notebooks that have actually created the book are free. It also has collab notebooks, so you can just run them in collab. The actual course website is Course of FastAI. You have the forums, you have Discord, and you have the documentation in docs.fast.ai. Well, that is it. It's just under an hour, 50 minutes more than I wanted it to be. And thank you very much. And if you feel like you want to hear more, let me know, and I'm happy to hear any kind of feedback. Thank you.